One of the big quests in organic chemistry has been in trying to be able to connect two carbons together. And a lot of what we've seen has been about connecting oxygens or nitrogens to a carbon, basically um, adding stuff onto a carbon skeleton. But how do you make the carbon skeleton longer? And in order to do that, you have to have a carbon nucleophile. And how exactly, I guess, would you go about making a carbon nucleophile? All right. So carbon nucleophiles, if you want to imagine the formation of um, something that has carbon, and then a carbon nucleophile is going to have a negative charge on it, I guess. Right? And so once it's got a negative charge, presumably it can do all kinds of attacking. Now, you can make a negative charge by deprotonating, and deprotonating a straight chain alkane is not easy, right? And I probably mentioned at some point that a straight chain alkane can be deprotonated by lithium metal. So you can actually make a lithium salt, and we'll talk about that. The lithium salts, just by throwing in a chunk of lithium, will put a negative charge on the ends, right? The most acidic protons. And again, we draw a very fine distinction because the protons on a carbon chain are really, really hard to pull off. The ones on the very ends are the easiest ones, so the terminal ones, so these and these. That's not really a great way to make carbon nucleophiles. At least it doesn't provide a lot of diversity. But a long time ago, a dude named Victor Grignard discovered that if you take pretty much any organic halide, and you throw in magnesium metal, and the magnesium metal, as we draw it right here like that, we can get rid of this, that's not very helpful. You end up making what's now called a Grignard reagent. And it looks like this. So the magnesium metal actually inserts itself in between the carbon and the halogen bond to create this. Now magnesium normally exists as a +2 state. So one way to look at this is essentially to look at it like this as a negative charge, and then a Br minus with a negative charge, and a magnesium 2 plus. That's one way to look at it. And so, but the thing is, the negative charge isn't going to swim around. You're not going to have any hydride shifts or proton shifts or anything like that. The nucleophilic carbon is wherever you started off with the bromine. And it's really convenient because what really this is just doing is it's just taking a pretty fragile bond, the carbon bromine or carbon chlorine. Doesn't work with carbon fluorine really. And you don't see it too often with a carbon iodide for some reason, even though presumably that would work just fine. But the Grignard makes this really wonderful, effectively C- charge, and it acts a lot like that. Okay, so the Grignard bond starts off as how does this look electronically, excuse me, I should say, very much like it's going like that, right? Because you've got the Br minus, so this is the electronegative system, is the Br, and so that's going to be pulling off electron density all the way up here, and so this is more of an electrophilic carbon. But once you transform it into the Grignard reagent, now things go the other way. All right, now the carbon is a nucleophile and not the electrophile. Now this carbon is ready to dance. All right, and so if you wanted to produce something, say, from an alcohol, if you wanted to, say, produce an methanol, all right, 1, 2, 3. Let's just say we will produce propanol. Propanol is this, all right? Let's get the right color. We want to make propanol from this, 1, 2, 3. So there's an alcohol here. And I told you your starting reagent, well, we had in stock is you got to start with this. All right, because that's what we got. We got 50 million tons of it. and you got to use it. It's cheap. How would you go about making this? All right, you get all the way to here. Well, you can imagine, looking at this like, all right, so there's a carbon and a carbon here, and obviously I could probably get another carbon if I just look at like cutting that bond right there. I could probably get to this and say a formaldehyde, right? Because that's a carbon. And we know if we take formaldehyde and we have a nucleophile attack it right there, it'll make the alcohol, right? So I would say that's probably the best route. So let's see how we have to do in order to form this. First, we would take ethyl bromide, and then we would we'd chuck in magnesium, just little magnesium strips, little tiny magnesium, nice, fresh, polished, shiny magnesium strips to form our ethyl Grignard. All right, that'll form. It's kind of a milky bathway. If you take advanced synthesis, you'll make quite a few Grignards. All right, great. And then formaldehyde. Sure, we'll take some formaldehyde. Okay, that's just carbon oxygen for the most part. And this is now a nucleophilic carbon, so it'll go pew, 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 and attack that carbon, kick that up there. All right, now we've got another carbon, so that's our ethyl group. All right, and what happens to the magnesium bromide is, that's going to turn into an O minus, right? So actually, let me just color this in so that it's pretty clear. Carbon, oxygen. And so now we've got the carbon here, and now that's an oxygen. That's an O minus. The magnesium bromide that used to be here, that's going to now be here, MgBr, because magnesium likes to have two buddies. It's got negative bromine. Now it's got that negative oxygen. And we just throw in an acid workup, H+, and that gives us propanol. All right, easy stuff. You just take a Grignard reagent and very quickly reacts with a carbonyl, formaldehyde in this particular case, which is a gas, and you end up with your propanol. So makes sense to me. You can also, like I said, do the same thing with lithium. If you just chuck in lithium and there's nothing there, it doesn't work so well. But if you I should say, if you just chuck in lithium with a straight chain alkane, it will make whatever is the lowest energy material. It gives you crap, right? But you'll make something really, really reactive. If you have a starting halide, it'll do the same thing. So if you have some sort of Br here and you chuck in lithium, you will end up with a lithium reagent. And those do the same thing, all right? So the lithium reagents, these are also basically a lithium plus and a carbon minus. Those are still carbon nucleophiles in principle. So the usefulness of this is that you can form carbon-carbon bonds, which is exactly what this is. If we look up here, right? I formed a carbon bond at that carbon, and that carbon form a bond. That's that bond right there. That's a carbon-carbon bond. I've also formed an alcohol from a ketone. So that's one way. That's another way to make an alcohol. So I can make an alcohol in that way. And it's a pretty great way to form all kinds of alcohols, as a matter of fact. So that's with formaldehyde, but if I wanted to make a secondary alcohol, then say I could take my methyl Grignard, MgBr, right there, and I could attack acetone. Why not? Stuff's pretty wicked. In fact, this will react very fast. This will serve as a negative charge right here. Attack right there, attack that pi bond, kick that pi bond up to the oxygen, and you end up with a new carbon-carbon bond that I will draw in orange, so that'll go down here. And the acetone now is this here with the O minus. All right, MgBr follows it along, magnesium bromide follows it along. And an acid workup, magnesium bromide doesn't survive the acid workup, but you do end up with a nice little alcohol right here. And they are pretty easy to make. Now that we're making more complicated molecules that take a couple of steps. Sometimes it's easy to imagine how you could do something through what's called a retrosynthetic analysis, right? So if I wanted to make something that was fairly complicated, usually what you would do is you imagine, say, I want to make two propanol. All right. So how would I make 2-propanol if I had to start off with something that, if I had to start off with a ketone somewhere, aldehyde maybe, and then a Grignard. And there are a couple of ways that I could do that. I could look and say, all right, so how can I make this? I can maybe make a bond there. So I could say, make this bond right here. That's fairly easy. I draw what's called a retrosynthetic arrow, which is sort of like these big gooey things. And if I wanted to make this bond right here, then I would have to start off with 3 carbons. That'd probably be my Grignard, MGBr. And then carbon something ethyl something or other, probably ethyl formate. So ethylaldehyde or acetaldehyde. Ooh, my goodness. Acetaldehyde is what that's called. And so acetaldehyde plus that will give me my 2-propanol. That's not the only way, of course. I can try that again, right? So if I wanted to do a simple retrosynthetic analysis here, I could also do this, right? I could break it along that bond. And so what I would be doing effectively is forming a new carbon-carbon bond, but I would start off with methane, so I can make a methyl Grignard, CH3MgBr, and start off with the aldehyde there. So what's that? 1, 2, 3, 4. 2, 3, 4, and then form that. So there are 2 approaches in my retrosynthetic, and I can write this out here, my retrosynthetic analysis to making these. And there's retrosynthetic analysis 1 and 2. And it's important when you do a retrosynthetic analysis to make the smallest little bits cleave in the most obvious spots you can and make those little cleavage points fairly small. And you can do all kinds of pretty neat tricks here. Now, Grignards, it's worth pointing out, they are C minuses, okay? So there is a limitation to how much you can really throw at a Grignard. So if you take a Grignard instead of an aldehyde, you take, say, a Grignard MGBr and say I wanted to attack carboxylic acid, right? And so you say, okay, well, that'll do that. And then what I'll end up with is something that looks like this. And I got an O minus and then an OH, and that's not going to happen. What you're going to actually end up doing is just deprotonating the acid, right? So Grignard reagents are C minuses, and C minuses are also bases because nucleophiles tend to also be quite basic, and bases tend to be nucleophiles, which means, and Grignards are a great example of this, if there is a proton that it can take, it will take it. So the outcome of this reaction would be fairly boring. It would be that ethane and O minus MgBr. All right, you would make ethane and the carboxylate salt, which is unfortunate. So how is it? But that doesn't necessarily mean that this shouldn't work, right? You've got a C double bond O. It should work. Is there a way? Is there a way around this? And as a matter of fact, science is incredible that way. You can actually convert a carboxylic acid into something fairly crazy called an acid chloride. You can also make them into esters, of course. So if you take carboxylic acid, all right, OH, and you convert it into an ester, well, and that would be with methanol. Let's just take methanol, OH, add a little bit of acid, all right, and you'll learn about this mechanism next semester. You can make the methyl ester. You can also use a compound called thionyl chloride. Just call it thionyl chloride. What that does is it converts it into an acid chloride. And that's also a mechanism that you'll learn about next semester. So you don't have to know how either of these are made. In fact, you don't have to even remember thionyl chloride or the esterification process right now. you have to know acid chloride and methyl ester, all right? Or an ester, all right? So this is acid chloride. This is a carboxylic acid, which you should know. And this is a methyl ester. The only one that Grignards really have a hard time reacting with is this one, thanks to that silly OH. Now, a Grignard will react with all of these. It'll deprotonate the carboxylic acid, but it will do nucleophilic addition to both the acid chloride and the methyl ester. And how does that look? Well, let's say you've got a Grignard. We're going to take our Grignard, MgBr, and we're going to throw in an acid chloride. All right, and actually, let's just go ahead and just do this. So we remember in our chemistry of the last talk that if we have an acid and then I have a chloride coming out here, they have a sigma bond, and then there's a pi bond. That pi bond goes around here, and it does that, right? And this, being a nucleophile that it is, will attack that pi bond and kick the electron density up there onto that oxygen. And that will give us our chloride down here, methyl, and then our corresponding ethyl group that just attacked in there, and then an O minus. And that MgBr satisfies that negative charge, all right? So what's that look like? Oh, naughty. It kind of looks like this, right? It kind of has this ClO, all right? O minus. Well, this is pretty easy. Actually, what this can do now is, you remember your carbenes? How you kind of had that weird interaction where you had a deprotonation and then there was an empty orbital? Well, this negative charge can actually just collapse back down into the pi system and kick off the chloride. All right? And then that creates your ketone again. Let's show how that worked again. All right? So what you end up doing is you form this again. What you end up doing is, let's go back up to this one. I'm going to re-illustrate it on this thing here. All right, because you just got to this point. So once you get to this point, that negative charge, it can actually reform the pi system if it comes back down here and then kicks off that chloride. All right, and then that will regenerate the pi system, except this time it will be an O. Now it'll have an ethyl instead of an alcohol. But here's the thing now. If you have one equivalent of carboxylic of Grignard, you can stop here. That's it. You can stop at your ketone. If you have a second equivalent of Grignard, this ketone, which is illustrated right here, can do this again. MgBr. Once again, can attack here. And this time, you will end up with a methyl. There's your first addition ethyl, second addition ethyl, and then the O minus. All right? Now there's no more else. It cannot collapse back down into a pi bond, and you end up here. And so acid workup, and you have this funny looking molecule. 1, 2, it's actually not that funny looking molecule, is it? Once you actually start drawing it out, it's just that. And that's your product. So you end up doing 2 additions to this ketone right here when you start off with an acid chloride. Same thing can happen when you have an ester, okay? So if you have an ester, you start off here, OCH3, a methyl ester. This CH3 can be a bunch of, ethyl ester, propyl ester, butyl ester, who cares, right? If the point is that you throw in a Grignard, MgBr, same thing can happen. This will come in here. Now the ester reaction is actually, this is a little slow. Kick that up there. All right, and then you end up with something that looks like O minus OCH3. And I'm going to actually color this in. So that's orange. Okay, so your ethyl group adds right there. And you remember that actually you've got two alcohols. You've got an OH and you got an O ester right here. Normally we say you don't kick off O minuses. So this methyl group, this methyl ether looking thing right here, should be safe. But you're treading into an area where you don't want to have two oxygens, or it's not very, when you see two oxygens attached to the same carbon, that's a pretty reactive carbon. And this particular, in this particular case, when you have two oxygens attached to the same carbon, they tend to do things that we normally tell you you shouldn't do, like kick off O minus. But that's exactly what happens. Is this negative charge comes back down to reform a pi bond, and it kicks off, boom, OCH3. All right, so that's pretty nuts by itself. You're kicking off OCH3 because normally you don't think of methoxide as a very good leaving group, and under normal conditions, it's a terrible leaving group. But in this particular case, you're throwing in basically a C minus, so an OCH3 leaving group's not too bad. The kicker, though, is that you form a new ketone. And in this particular case, when you do the reaction with an ester, this ketone is way more reactive than the original ester. So even if you just try to throw in one equivalent of ethyl magnesium bromide, it doesn't matter. Because the second you form this butone, this ketone, another of these friggin' Grignards are going to come in, MgBr, and they're going to attack, and you're going to end up with, once again, forming two carbons. That's connected to your original carbon, and that has an O minus, and then a CH3, and then that's going to be the other Grignard. All right. So you've got two additions of Grignard. That's an MgBr. Acid workup gives you the same product. All right. This is essentially an unavoidable reaction when you work with esters or acid chlorides. Although acid chloride is the original acid chloride, this is by far the more reactive species. So acid chlorides are extremely reactive. Methyl esters will react. The most reactive, of course, is the acid chloride. You take acid chloride, you throw it in water. Water will attack it. Methyl esters are much more stable. Okay? So in this case, this is what you want to remember, right? That carboxylic acids, they just get deprotonated by Grignards. Acid chlorides add twice, and methyl esters add twice. They both add twice, right? And you end up with something that looks like these down here, all right? So that's an important distinction between these two. Grignards are very powerful, so they can react with all different kinds of electrophiles, even relatively stable ones. So peroxides, for instance, peroxides are not charged, but they're very strained rings. So if you throw in my favorite Grignard of all time, ethyl Grignard, they will attack, and they'll attack on the least tendered side, okay? And they'll attack there, and they'll open up an epoxide ring. So this can be an SN2 type reaction where you end up with, and we should color this, right? We should color our Grignard. I can just erase that because I don't want to cause confusion. And then that gives you, now that's opened. All right, so that pops right open. And what was originally here were two hydrogens. Right? And those two hydrogens are still there. And you see how I've made a new carbon-carbon bond, and then an acid will work up, protonates that, and that's how you get your alcohol, okay? Now, I should be very specific. Grignard reagents are good bases. They love to be nucleophiles, but they are very good bases because carbon CH bonds, you know, you think a pK of 50, they're deprotonated, they are like crazy reactive. So this works well so long as you have no heteroatoms, no OHs, no NHs, none of that, all right? Because the Grignard will go deprotonate it. It's like a beta fish, okay? You know, beautiful, majestic beta fish. And they're good for one thing, staring at. Grignards are great for forming carbon-carbon bonds, but if you put them in there with an H, just like if you put a beta fish in with another really pretty finny fish, that just rip all the fins off. That's what Grignards do. They're not beautiful in any way whatsoever. They're just really vicious nucleophiles and bases. So you cannot go off and throw them in. So if I were, this is a trick. If I said, ooh, this is a favorite trick of organic profs. And they say, and I've got GBrCH3. What is the reaction? And then, you know, half the class is going to be like, oh, well, look at me, an intellectual knows that it's going to be this. Except that's going to be wrong because the actual product of adding a Grignard reagent to an alcohol, no matter what, is just to deprotonate the alcohol. And then the professors are always just laughing because they think that's funny. It's a very valuable lesson. Do not try to use a Grignard on anything that has an NHOH, SH, nothing like that. Doesn't give you the product you're looking for. Don't try to use a Grignard in water. Don't try to use a Grignard in an alcohol solvent. Don't feed a Grignard after midnight. And never give a Grignard a bath. So that's sort of your limitation. Grignards are great nucleophiles, and if you have a reactive little bitty right there, they'll pop open. You got a ketone, they'll pop open. Esters, they'll add twice because they're a little bit vicious. You know, they're good that way, but you know, they will deprotonate things. Now they'll add to anything. So you know, just because you have an OH or NH, you know, that's another one you can't really work with. Double bond, nope, it'll deprotonate that. But if you start oxidizing these things to like imines, right? So, you know, an amine is, it looks like that, but an imine is like a double bond nitrogen, right? It'll react with your imine, right? You'll have a Grignard, and a Grignard can react right there. It will react with nitriles. Well, often Grignards are what I think of when I think of nucleophiles. It'll react right there. It'll react with pretty much anything that has a double bond. And it will always react, all right, on one side of these. It will always react at the most electron deficient side of a structure. So if you have, say, carbon dioxide is a great example. OCO, right? And so you take a Grignard, take a aromatic ring. You can do this, benzyl Grignard. Add in some magnesium. You make the benzyl Grignard, MgBr. Throw in some carbon dioxide. That'll attack the carbon. Carbon will kick that over. And you'll end up with carboxylic acid acetate, all right, because it'll be O-. So, yeah, Grignards are so bad they will even react with carbon dioxide, all right, and that's really great because that's a great way to make carboxylates, right? And then, of course, you add an H+, and then you can get benzoic acid out of it. So, and you'll notice in this particular case, you'll notice that it reacts with the carbon, the most electron deficient, the most comparatively electronegative of those two reagents. All right. If you have a Grignard and you don't want it anymore, for some reason you don't want your Grignard anymore, you can, of course, throw it in water and, you know, it'll make the Grignard sad. You just put H plus and that carbon is just like yoink. And now you're back to having CH3, CH3. Very easy way to kill a Grignard. All right. If you want to eliminate, or I guess if you really think about, you know, you've got a halide, an alkyl halide, and you want to have, you want to end up with just that, you know, your retrosynthetic analysis, I guess, would lead you to be, this is a very wasteful way of doing things, just throw magnesium turnings, I guess, so magnesium strips, and you make your Grignard, and then you throw in an acid. Seems like a waste to me, but that would be a way of generating that. And you can do the same thing. So with a source of hydride as well. So if you have a Br here, you can actually throw in aluminum hydride as well. Again, I'm not quite sure. So lithium aluminum hydride, why anybody would do this? Lithium aluminum hydride will react with that to give you your final this. I think these are all instances of you should be cautious. As a graduate student, I was not thinking. I tried to use lithium aluminum hydride on I can't remember what it was. It might have been something along these lines. It was a brominated, and then it was an aldehyde or something like that. And I was like, I'll just reduce that with lithium aluminum hydride or something. And I, of course, ended up with just the alcohol. Lesson learned. You cannot do that. You can also not do that with palladium on carbon hydrogenation. That'll also pop your bromine off. So keep these things in mind, right? Source of hydride, source of carbon nucleophiles. They can be a little tricky sometimes.